All right, welcome to the 4.6 Fuck My Life episodes. We're drawing graphs of functions, and we are going to use everything we learned in algebra, like finding intercepts and domains and end behavior. We found an upgrade to end behavior here. We also have derivatives that will show us local maxes and mins. It will show us concavity, regions of increase and decrease. It's all getting thrown in, and we can graph this shit a little bit better. So let's just throw all the steps up at once on the screen. If you want to just pause it, write them down, and then fast forward through this part till we get to a problem, go right ahead. We want to start off finding the domain. When we find the domain, we'll find out later on we're going to use the domain to find vertical asymptotes. These go together. But the book wrote them in this order, so I'm trying to do the order the book used. We'll find any x and y intercepts. These are all algebra steps here. We will determine end behavior with limit as x goes to infinity or negative infinity. We'll take advantage of what we've been doing in this section, as well as what we did in the getting ready for like end behavior of polynomials and stuff like that. When we're doing this, we want to note any horizontal asymptotes or oblique asymptotes. Remember, oblique asymptotes this is when the top x over m plus dot 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 x to the n plus dot 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 m equals n plus 1, the exponent. The top is 1 degree higher. After we have that, we'll have a vertical asymptotes. We have a horizontal or oblique asymptotes. We have intercepts. We're going to find the derivative, find critical points. We'll use that to find regions of increase and decrease, and then find local extrema, our max or min. Max or min. And when we do the second derivative, we can do concave up and concave down. That helps us with curvature. And we can also verify our local extrema with it. And you'll notice number 7 is written really small because I don't think the book even says in number 7. But number 7 is take all that shit, put it together, and graph it. All right? Let's start our first FML problem. We're going to start off with a simple one, polynomial. F of x equals x plus 2 squared times x minus 1. This is a polynomial, so polynomials have infinite domain. They have no problems anywhere. So, yay! Our intercepts, x-intercept is when you set y equal to 0, which is f of x. So if we do that, we get x equals negative 2, which means, and it's squared, so we have a multiplicity of 2. That means at negative 2, it's going to, when it hits the, it's like a, it's not just a root, but instead of crossing there, it's either going to bounce off like that, or it's going to bounce off like that. It does a bounce, okay? Make sure you look at the getting ready stuff for reminders of multiplicity. We also had x equals 1. And so that gave us these two coordinates right here. Negative 2, 0, and 1, 0. The y-intercept is when x equals 0. So if you just plug it in, you get the constant at the end. 2 squared times negative 1 is negative 4. So those are more points we have. And I'm going to, in fact, I'm going to do a little highlighter on them, leave them like that, because you're going to want them later on. Okay? And in fact, I rewrite them later on when I get to the graphing. Next step is end behavior. So we're going to take the derivative, or not the derivative, we're just doing limits. If we do the limit of it, remember the limits of like f and times g, we can separate it. We can do the limit of each one separately. And there's an easier way to do this. We could just multiply it out as we're going to do in a second. But this is a great way of checking it. When this happens, we have infinity. They're both going to infinity, so we end up with an infinity. So it's going up, up, and away to the right. When we do negative infinity, we can split it up. Negative infinity squared would give us positive infinity. But negative infinity not squared is negative, so a negative times a positive is going to give us a negative. So it's going to do some stuff like that there. Okay? The next step is a little easier if we expand f of x. So I multiplied it out, collected terms, and I got f of x equals x cubed plus 3x squared minus 4. Here it's also easier to see what n behavior looks like from algebra. And we talked about this in the getting ready section. When n was odd, x to the n, this looks like x to the n here. When n is odd, it does behavior like this at the ends. If n is even, for even, it does either that, looks like a U, or it's downward on both sides. Okay? And we cover, that shows up in the getting ready for this, or 4.5 also. 4.5 getting ready is going to be your best friend. Okay? So we need vertical asymptotes. Polynomials don't have vertical asymptotes. Then we want to do the derivative, and now having it in this f of x form makes it doing easier. We don't have to do the product rule or chain rule here. If you wanted to not expand it out like I did and do the product rule, chain rule kind of stuff to do the derivative, you're more than welcome to, but I actually think this is easier. So the derivative of x cubed plus 3x squared minus 4 is just 3x squared plus 6x. We set that equal to 0 to find our critical points. I factored. So this gets set equal to 0, and I get x equals 0. X plus 2 gets set equal to 0, and I get x equals negative 2. It just so turns out, notice that that is our, we have those two listed up above, here and here. So I already knew the values of the points, the not just critical value, but critical point, but you can recalculate them using this polynomial here, plugging in 0 and negative 2, and you will find you get 0, negative 4, and negative 2, 0. So we are going to make a sign chart now. We're going to plug in our critical points there and there. They give us a little boundary kind of thing. We do some test points on the derivative. So 3x, if I plug in like negative 10, I get negative for 3x. I get negative for x plus 2. So a negative times a negative is a positive. Positives go up. When I do negative 1, negative in the negative 1 and 3x is a negative. Negative 1 plus 2 is a positive. It equals 1. So the overall region is a negative. And if I stick in 10, they're all positive, which means we're going back to increasing. So this is doing some wavy shit like this. In fact, let me try to time it better where it's like at the negative 2, now it's coming down. And at the 0, it's going back up. It's doing some stuff like that. Okay? It is worth writing down regions of increasing and decreasing. Identify your local max. I can see since it's going up and then coming down, negative 2 is the local max. And at 0, it's going down and then coming up. 0 is the local min. I will use on the next step, we are doing the second derivative, so we're going to use that. Take the second derivative, we get 6x plus 6. We set it equal to 0. We get x equals negative 1. I actually plugged it in to find out the coordinate because that's an inflection point. And I wanted to have that spot on the graph plotted pretty well. So I put that in there. So when you're doing negative 1, let's see. So I didn't do the fucking sign chart. Oh, yeah, I did. There's the sign chart. So negative 1's right there. Notice for testing my either side, I used my critical points from the first derivative. That way I can verify a local max or min. Makes it easy. Negative 1, when you plug it into the second derivative, is concave down, which means opening downward. Does give us a max, like we said. And plugging in 0 gives us a 1. That gives us a concave up, which would be a local min. So now we've got all the stuff. We're going to put it together. You know what? Maybe I can delete that graph and draw it live. Hopefully that did it without you guys seeing it. Shit. There we go. So I made my graph. I plotted my points. These were all my intercepts. So there, and there. Maybe I'll still do this. Use the highlighter for the intercepts. I had an inflection point at -1, -2, so that was right there. And I know that I am increasing, and I know the end behavior looked like this. That was our end stuff. So down on the left and up on the right. I know -2, 0 is a max. So if it's going down to the left, it's doing something like that. And it's a max, which means it's got to come back down and go down like that. The inflection point is where the curvature starts to change. So I'm going to do blue for concave down. And then when I do concave up, it's concave up for the res. Notice that over here, concave up. Oop. So we go down. This was a local min. And it starts going up. It crosses there, and it just keeps going up. So that would be the graph of this. All right, I'm going to pause this video. We got 2 more. This was the polynomial one. This was the easy one. Next up is FML2, your second fuck my life graphing problem. Oh, the in class is filled with these two, isn't it? What did Hefe do? Stop recording.